The theory of plate tectonics was first discovered in 1915 by German meteorologist and geophysicist Alfred Wegener, when he proposed the concept of continental drift. He stated that a long time ago, our continents once formed one large landmass called Pangaea. Over millions of years, Pangaea broke apart and moved into the positioned continents we know today. At first, scientists were skeptical of Wegener's theory, claiming that there was no force powerful enough to move these large landmasses huge distances, and that Earth's crust was simply too brittle and stiff. But Wegener did not give up on his theory and compiled data and evidence to support his claims. The theory of plate tectonics not only explains the formation of continents and the characteristics of Earth's crust, but it also explains the formation of mountains, volcanoes, earthquakes, and oceans. Through observation and analysis, Wegener concluded that the continents once fit together like puzzle pieces to form Pangaea, then traveled apart because of continental drift. This can be shown through arranging South America and Africa together like puzzle pieces. The east coast of South America matches up with the west coast of Africa, fitting together almost perfectly. Wegener also discovered very similar fossils on the coasts of the two continents where they were once connected. The continental drift theory is also supported by certain geographic features. Pangaea once had huge mountain ranges, but as the continents drifted apart, the mountains were separated. This can be seen with the Appalachians of the U.S. East Coast and the mountain ranges in the British Isles and Scandinavia. These mountains have very similar structure and composition, further supporting Wegener's theory of continental drift. There are a total of 17 tectonic plates, with 5 major ones that form most of the Earth's crust. These plates can make up a continent, an ocean, or both. How these plates interact with one another is the force behind continental drift and is responsible for many geographic features. These plates make up the outermost layer of the Earth's crust, with the upper part of the mantle underneath, called the asthenosphere. The asthenosphere extends 200 miles below Earth's surface and is made of molten rock and has plastic-like properties. This allows the tectonic plates to move around easily and interact with each other. Oceanic plates are made of basalt, which is very dense and brittle. On the other hand, continental plates are composed of granite, which is more light and buoyant. The composition of these plates play a big factor in how they interact with each other. There are 3 kinds of boundaries where tectonic plates can meet: convergent, divergent, and transform boundaries. The first kind are convergent boundaries, where 2 plates travel toward each other and collide. When 2 oceanic plates converge, one dives beneath the other in an act called subduction. As the plate subducts, it is heated by the asthenosphere, and the newly molten rock slowly rises to the surface. This can form mountains and volcanoes when the molten rock, called plutons, pushes through the surface. When a continental plate and the oceanic plate are converging, the oceanic plate subducts underneath the continental plate because of its composition. The dense basalt that makes up the oceanic plate is much heavier than the light granite, and therefore subducts easily under the continental plate. As the oceanic plate is subducting, it causes tension against the continental plate as it bends against the force. Eventually, the tension becomes too much and the overriding plate will snap back into place. This upward thrust causes huge earthquakes called megathrusts and tsunamis along the coast. The continental plate is thrust upward, creating a huge wave that travels miles until it hits land. The last kind of convergent boundary involves 2 continental plates. As the plates move towards each other, no subduction occurs because they are equally dense. Instead, they collide together and push up, forming mountain ranges like the Himalayas over thousands of years. These fold and thrust faults cause distinct continental features and occur all over the world. The second kind of boundary formed by tectonic plates are divergent boundaries, where plates move away from each other. 2 oceanic plates that are diverging are creating deep crevices in the Earth, allowing hot magma to rise from the asthenosphere. The magma cools and hardens at the point where it reaches the surface, forming oceanic ridges deep underwater. A notable oceanic ridge formed by divergent boundaries is the Mid-Atlantic Ridge, which can be seen from space. When two continental plates meet at a divergent boundary, they form continental rift valleys. The molten lava rises up and forms large hills or mountains that surround the valley. The Red Sea was also formed from two diverging plates. The gap that was created was big enough to form a sea, and the space was filled with water. The third and final kind of boundary formed with tectonic plates are transform boundaries, found at both oceanic and continental plates. Here the plates slide past each other vertically, causing tension as they catch on each other. The grinding plates move past each other very slowly, but with enough force and tension, they can slip and a shallow focus earthquake will occur. The transform boundaries can also be called strike-slip faults because the plates strike, then slip past each other violently. The most famous transform boundary is the San Andreas Fault Line, which runs through California. The San Andreas Fault is the most famous boundary in the world. It is a transform boundary that runs along the edge of California where the Pacific Plate and the North American Plate meet. It is the largest of a system of faults, with smaller ones named Hayward, Calaveras, Garlock, and Imperial. It runs through the city of San Francisco, where it was discovered when a major earthquake struck in 1906. The San Andreas Fault runs 800 miles along the California west coast, and it dives 10 miles deep into the crust. It moves at 2.5 inches per year and has a total displacement of about 350 miles. Large, destructive earthquakes occur at about 150-year intervals, but moderate-sized ones that can still cause damage can occur at any time, making the San Andreas Fault very unpredictable. The 1906 earthquake occurred on April 18th, scoring 8.3 on the Richter scale. The earthquake also started a large fire, causing billions of dollars in damage. At the time, it was thought to have claimed about 700 lives, but after further investigation, we now estimate it to be 3 or 4 times more than that. The shaking lasted 45 to 60 seconds and could be felt from up in southern Oregon to down in Los Angeles. The 1906 quake gave way to much of our knowledge of earthquakes today, like the discovery of the elastic rebound theory. It has left its mark on the land, leaving huge displacements up to 21 feet wide. Some of these marks can be still seen today, with evidence of displaced fences and roads.